Hi, welcome to Elkchemist Chemistry, another video looking at electron configurations. By the end of this video, I can guarantee you will know the shapes of some orbitals and also be able to construct electron configurations for various atoms, ions, and transition metals. In fact, you'll even be able to use this grid to work out the electron configurations of some pretty advanced elements from the periodic table. Let's get started. Firstly, I'd like us to wrap our heads around that term orbital. An atomic orbital is a mathematical function that describes the wave-like behavior of electrons. Like many other small particles, electrons exhibit both wave-like and particle-like behavior. It can be seen as representing a probability distribution for finding up to 2 electrons in a specific region around an atom's nucleus. In other words, it is a region of space where we are highly likely to find up to 2 electrons. Orbitals come in different shapes, dependent upon the way the mathematical function describes that probability distribution. Perhaps the simplest shape we come across is that of the S or sharp orbitals. They are simply spherical regions of space where we'll find up to 2 electrons. Next up, we have the P or principal orbitals. These orbitals actually follow the Cartesian axes, the X, Y, and Z axes of three-dimensional space. These orbitals have a more dumbbell-like appearance, and again are regions of space where we are likely to find up to 2 electrons inhabiting. And then we have the D or diffuse orbitals. Now you can see these are much more complex multi-lobed orbitals, and they don't necessarily always sit exactly on the X, Y, and Z Cartesian axes. So for dxy, dyz, and dxz, these actually sit between the Cartesian axes and are effectively like 2 p orbitals intertwined. Whereas the dz squared and the dx squared minus y squared, these ones do sit on the Cartesian axes, the z-axis for dz squared and the x and y axes for dx squared minus y squared, but the dz squared in particular also has this additional ring of possible probability where we could find that electron density. So these are becoming quite complex in their distribution. And at this point, you're probably asking yourself, what is the point of all these orbitals anyway? Well, don't forget, orbitals are simply where we find electrons. And actually, electrons can't exist around the nucleus at any random energy level. Instead, we would say that there is a quantized system to where we can find electrons. A quanta is a discrete and well-defined amount of energy. And according to the Bohr model of electron configurations, electrons exist only at very set, quantized energy levels, or as we used to call them, shells, around the nucleus of an atom. The lowest possible energy state or level we can find electrons in is the lowest principal quantum energy level. That is n equals 1. As we grow to larger electron systems with more electrons around the atom, the first energy level is filled with electrons and can take no more capacity, and we have to move up to the next highest energy level, the next principal quantum energy level, which is n equals 2, and so on as we get more and more electrons around the atom. So this is probably quite familiar to you as what looks like the Bohr model of electron configurations from GCSE. However, one thing to note about these principal quantum energy levels, which we used to call GCSE shells, is that as you move up to higher energy states, they begin to get closer together to each other. The energy levels begin to converge. And if I exceed all the possible energy levels, I will have ionized that atom, losing the electrons from the system entirely. But don't forget for later on that as we go up through the principal quantum energy levels, n1, 2, 3, 4, 5, etc., that eventually they're going to get very close together, and that becomes important for how electron configurations work later on in the video. And now we come to the fork in the road, the true divergence from the GCSE Bohr model. It turns out that each principal quantum energy level, or what we used to call shell, can actually contain a number of sub-levels of energy, which are actually where we find those s, p, d, and f orbitals residing. There actually is a hierarchy to the energy of these sublevels. So s sublevels, which contain just one s orbital in them, are generally the lowest energy sublevels in existence. Slightly higher in energy are p sublevels, which contain 3 p orbitals at that level, because we have the p orbitals on the x, y, and z Cartesian axes. Slightly higher in energy again are the d sublevels, which contain 5 d orbitals, those multi-lobed complex orbitals we saw earlier on. And finally, the highest energy sublevels we can find are f sublevels, which contain 7 f orbitals. And f orbitals are even more complex in shape distribution than the d orbitals. Now this table goes through what we might find at some of these principal quantum energy levels in terms of sublevels present, orbitals present, and how many electrons we're going to find at that particular energy level. So n equals 1 is the lowest principal quantum energy level in terms of energy, and it only has one sublevel present at that particular energy state. That's the 1s sublevel, which only contains one s orbital. So there are only 2 electrons found at this particular energy level. This corresponds with the first period of the periodic table. We find hydrogen and helium. N equals 2 is the next principal quantum energy level up in terms of energy, and it has a 2s and a 2p sublevel. So the 2p sublevel has 3 p orbitals present. That is the x, y, and z Cartesian axes p orbitals. So we have 2 electrons in the s orbital and 2 electrons in each of the 3 p orbitals, creating 6 electrons total in terms of that sublevel. So there are 8 electrons able to exist at this particular principal quantum energy level 2, again corresponding with period 2 of the periodic table. N equals 3 is the next principal quantum energy level up, and that has even more energy, and so has a 3s, 3p, and a 3d sublevel able to exist at that particular principal quantum energy level. So again, there are 2 electrons in the 3s, there are 6 in the 3p for the 3p orbitals found in that 3p sublevel, and there are actually 10 electrons able to exist in the 3d sublevel because that has 5 d orbitals, and each d orbital can contain 2 electrons. That's 10 electrons total. So there are 18 electrons able to exist at principal quantum energy level 3 in terms of energy. Now, principal quantum energy level 4 has a s, p, d, and now a 4f sublevel as well. So that's 2 electrons in the s, that's 6 in the p, that's 10 in the 4d, and the 4f contains 7 f orbitals. Each orbital able to contain 2 electrons, so 7 times 2, 14. That's 14 electrons able to exist in the 4f sublevel. So that is 32 electrons total able to exist at principal quantum energy level 4. Now, while this table is both eloquent and very logical, unfortunately, evidence from ionization energy experimentation does not support that this is exactly how electron configurations actually work. What we find sometimes is when we're stripping electrons away from atoms, there are sudden jumps in terms of energy requirements, which would indicate we're dropping down an entire principal quantum energy level, or perhaps a sublevel, which doesn't seem to correspond with the pattern of electron configuration illustrated by this simple leveled approach. Something else is going on, and I'm going to show you a diagram which hopefully should explain exactly what's happening here. Hopefully you remember that I said that as we go up through the principal quantum energy levels, they begin to get closer together. That becomes important as we rise up through those levels. So when we go from principal quantum energy level 1 to 2 to 3, the key point I want to focus on is principal quantum energy level 3. Don't forget that contains a 3s, a 3p, and a 3d sublevel. Now, just above it is principal quantum energy level 4, which is close in energy. And look what happens. The lower energy 4s sublevel has actually dipped below the energy of the 3d sublevel when it comes to figuring out our electron configuration. Because of the proximity of the principal quantum energy levels to each other in terms of energy, when we start to split them into their corresponding sublevels, we get some convergence of those sublevels. They're so close together in terms of energy that it begins to create a slightly more complex pattern when it comes to which electrons are found at which particular energy state. So sometimes there are going to be overlaps and convergences, which means we can't just have a very nice linear 1, 2, 3, 4, 5, 6, 7 energy pattern. Instead, it's a bit more convoluted, and there are some overlaps between sublevels dipping into other principal quantum energy levels, and we must be aware of that. Now, at the end of the video, I'll show you exactly how to deal with that, but just something to keep in mind. And we're going to be looking particularly at situations where this 4s sublevel is below the energy of a 3d sublevel when thinking about building up electron configurations from scratch. Now, I know you're probably champing at the bit to get stuck into these electron configurations, but I want to introduce 3 simple rules we're going to use to ensure we do this successfully. The first is known as the Aufbau principle. Now, Aufbau is a German word for building or building up. So when we're building up an atom's electron configuration, we're going to make sure we start with the lowest energy orbital first and build upwards from that foundation point. Rule number 2, Hund's rule. A sublevel will fill orbitals within that sublevel with single electrons in each available orbital before trying to pair up electrons within those orbitals. This will be reducing internal repulsion experienced within those orbitals, which is more energetically favourable. And the final rule is known as Pauli's exclusion principle. Only two electrons are allowed to occupy any one orbital, and they must possess opposite spins, i.e. they're actually physically spinning in opposite directions to each other, as again, this is going to improve the stability of the system in terms of it holding those two electrons comfortably within the orbital itself. Now, to represent that in our diagrams later on, we're going to have half arrows, one pointing up, representing a particular direction of spin, and one pointing down for the opposite direction of spin, clockwise and anti-clockwise, for example. Alright guys, now we come to our first worked example. And for each of these worked examples, I'm going to take you through how many electrons there are in the actual atom itself in terms of how many electrons present. I'm going to take you through a box and arrow diagram to represent the electron configuration, convert that into a shorter hand version, and then an even shorter hand version using a noble gas configuration to show you all three ways you could represent these electron configurations. Okay, let's begin. So we're talking about a sulfur atom, where its atomic number 16 tells us we have 16 electrons available to play with. Let's start off with that box and arrow diagram. So I'm going to count them in. Hopefully you can work along with me. I've got 1, 2, 3, 4, 5, 6, 7, following Hund's rule. 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons present in that sulfur atom. So again, I've followed Hund's rule in this 3p sublevel, singly occupying the orbitals before I pair up, following Aufbau's building principle, starting from the lowest energy orbital up, and Pauli exclusion principle. Each box represents one orbital, and I can only put 2 electrons in any one orbital. Let's convert this from the box and arrow representation into a more shorthand version. So I could write this as 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 4. These are effectively equivalent to each other. Now I could be even more shorthand, because effectively what I have here is the electron configuration of a neon atom plus this 3s2 and 3p4 section afterwards. So I could write square bracket neon, which means the electron configuration of a neon atom, plus the 3s2, 3p4 additional occupied orbitals and sublevels. So these three ways of writing are all equivalent to each other, simply slightly longer version, shorter, and shortest or shorthand version. Right guys, let's look at another worked example of an atom. Our second worked example is for calcium, an atom of calcium. Again, I've shown the atomic number is 20, so we've got 20 electrons to play with around this calcium atom's nucleus. I'm going to work through this sequentially, and hopefully you can work along with me. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 electrons all used up. And so I convert this into a more shorthand version. This would be the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I could shorten this even more, so I could say this is the electron configuration of an argon atom, up to here for the noble gas configuration of argon. So I could write square bracket argon's electron configuration plus the extra little bit, which is the 4s2, or the outermost valence electrons of the calcium atom. That's our second worked example for an atom of calcium. Okay, the third example I have here is for an ion, an oxide ion. Now the difference here is the original oxygen atom had 8 electrons, but when this oxygen atom reacted with something else to gain 2 electrons to form an oxide ion, I've got to consider those electrons are now there. Those 2 additional electrons through the formation of the oxide ion need to be accounted for in my electron configuration. So again, keep up with the counting guys, hopefully this will make sense. I have 1, 2, 3, 4, 5, 6, 7, 8. Now those electrons in red are the original electrons found around an oxygen atom. Now to consider the 2 electrons additionally giving this oxide ion its 2- charge. So that would be 9, 10. So we actually have 10 electrons when we include those 2 additional electrons for the ionic charge of the ion itself. So if I write that as a more shorthand version, that would be 1s2, 2s2, 2p6. Okay, so actually that's the same as the electron configuration of a noble gas. That is the same as the electron configuration of neon. So what we're saying here is this oxide ion has an identical electron configuration to the noble gas configuration of neon. Let's flip the scenario around and look at a magnesium 2+ ion. This time we have a positive ion which has lost electrons to form that overall positive charge. So originally a magnesium atom had 12 electrons, but we've lost 2 to give that an overall 2+ charge. So we need to remember now that we had 12 electrons originally, but we are taking away 2 to produce our 2+ overall charge. So actually, in reality, there are only 10 electrons around this particular magnesium 2+ ion. So let's keep a track of this as we work through. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the magnesium ion rather than the magnesium atom. So writing that out in a more shorthand form, 1s2, 2s2, 2p6. Interestingly, this positive ion has also produced a neon noble gas electron configuration. Our next work example is an interesting one. We come to a transition metal, okay, iron. Now this is the first time that this comes into play, okay, that we now have an atom which is big enough to have an electron configuration where we are putting electrons into a 3D sublevel for the first time. Now the 3D sublevel is actually going to be above the 4s sublevel, which is dipped below due to the proximity of the principal quantum energy levels getting close together and that splitting of energy due to the sublevels. So we've got to remember that actually when we're following Aufbau's building principle, we're going to be filling up sequentially, and when we get to 3p, we're not going to go straight to 3d. We're going to remember that actually it goes 3p, 4s, 3d, looking at this list here, 1s, 2s, 2p, 3s, 3p, 4s, then 3d. So that's what I've represented here, remembering that actually according to that arrangement, the 4s is going to be lower in energy when following Aufbau's building principle than the 3d sublevel. We have 26 electrons to play with for an iron atom. So again, I'm going to count along with me up this box and arrow diagram, then convert it to shorthand, then the noble gas configuration. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. Converting that into a shorthand version, that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. 1, 2, 3, 4, 5, 6. Again, we could do a noble gas configuration here. Okay, so again, we can see we've got the argon configuration plus the bits at the end. So I could write square brackets argon plus the 4s2, 3d6. Additional valence electrons in the 3d6. And there you have it, guys. The next 2 elements are a bit of a curveball, chromium and copper. Now, if we were following through what we've seen in the video so far in terms of electron configurations, well, then we would assume that the end of the electron configuration for chromium would be 4s2 and 3d4. However, it's not. Chromium does something very interesting. Because of the proximity of the 4s and 3d sublevels, being so close to energy, and actually at times the 4s sublevel can actually be treated as being a higher energy state than the 3d once it's occupied with electrons due to various relativistic interactions and internal repulsion having an effect as well. It's actually more energetically favorable to not put 2 electrons into that 4s sublevel to avoid that additional repulsion. Instead, chromium is better served energetically putting 5 electrons singly into each of the orbitals in the 3d sublevel, and that overall gives it an energy kickback, if you like, and is more energetically favorable than not doing that. So it turns out chromium actually finishes as 4s1 3d5 rather than 4s2 3d4. So I'm going to write that out for you now, and just one to remember for the future. So 24 electrons to play with, not forgetting I'm only going to put 1 electron in the 4s sublevel. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, skipping 1, 20, 21, 22, 23, 24. In other words, that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Again, we could use the argon as well. Ar, then 4s1, 3d5. Half filled D sublevel, clearly present throughout. Copper follows a similar sort of pattern or trend to chromium in this case. Rather than it ending 4s2 3d9, instead it finishes 4s1 3d10 because for this particular element it is more energetically favorable to have the paired orbital in the 3d sublevel rather than the 4s sublevel, and it provides greater energetic stability for this particular atom in doing that. So again, I'll follow it through, counting it out, then transferring it to shorthand, and even shorthand with the noble gas configuration included as well. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. That would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Or Ar, and then the bits at the end, 4s1, 3d10. Wicked, guys. There's one more left. Going to finish here with a transmetal ion example, and again, something to be aware of here, which can sometimes catch out students, again, due to the proximity of the 4s and 3d sublevels in terms of energy, and the nature of the interaction between the two sublevels, particularly given the shape, the complex shape of the 3d orbitals compared to the spherical shape of the 4s orbital. When we think about these occupied electrons, it turns out that when we look at these from an ionization energy point of view, it appears to be the case that the 4s electrons are actually removed before the 3d electrons when we are ionizing and removing electrons from transition metals. So I'm going to remember to not include electrons in the 4s sublevel, remove electrons from the 4s sublevel for this particular metal ion. So let's put this into context, guys. An iron atom has 26 electrons normally, but the 3+ iron ion, hard to say that, has lost 3 electrons to form that 3+ charge. So we have 26 electrons originally, but we're going to take away 3 for the 3+ overall charge of the ion itself, leaving us with 23 electrons remaining in the system once we account for that. Going to count them across, but I'm not going to put electrons in that 4s sublevel because that's when they've been removed from first. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Removed from here, 19, 20, 21, 22, 23. So we've also lost an electron from a 3D orbital, 2 from the 4s, taking us down to 23 electrons total. So let's write that out in the shorthand version. That would be 1s2, 2s2, 2p6, 3s2, 3p6. No electrons in the 4s orbital at all. Straight to 3D, and there's only 5 electrons left. So 3d5. In other words, A are 3d5. And that's the final example for the day, guys. Congratulations, you've just done a whole plethora of electron configurations. Good job. I want to take you through one last thing, which is a little bit of a cheat that can help you work out electron configurations of some pretty ridiculous elements. Let's have a look at that. So this grid method allows you to work out the electron configurations of some pretty huge atoms in terms of electrons in the system. Let me show you how this works. You effectively just run your finger along the direction of the arrows and keep a track of how far you've come, and you can work out the configurations of some ridiculously large atoms in terms of electrons available. Follow through this with me. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. So we could, in theory, work out the electron configuration of electron systems that go well beyond anything we've seen before, with hundreds of electrons present without making a mistake. That's pretty epic. Guys, thank you so much for listening to the end. I hugely appreciate it. I really hope this video has helped you to master and feel like you can really conquer these electron configurations more effectively in the future. And as always, if you found the video useful, please think about giving it a like. You can subscribe to the channel to get access to our latest videos. We put out content on a weekly basis, and your support is hugely appreciated. So thank you so much. Take care. Bye now.